in this camera, so you are correct. But I have not read this because I find this. I think was it's just like I'm like, okay, I can watch it.
Okay, we are going to start the tutorial in a couple of minutes.
Wow. Getting I think we like to just level up geekiness like
Okay, I think we should get started. It's slowly coming.
I feel like 2 minutes and then we'll.
Okay, let's get started. Hello, everyone. Welcome back for the second tutorial of the conference. So the tutorial is about the mathematics of continual learning, which is a very interesting topic, presented by Liangzu Peng and René Vidal. So Liangzu is the PhD student at Peng here, and his advisor is René Vidal, who is going to present this tutorial with Liangzu, and he's remote right now. And Liangzu received his MS degree from Shanghai Tech University and his BS degree from Zhejiang University. His current research focuses on continual learning, but as you all already know, he's also one of the local chairs, and he's doing an amazing job with Uday in putting together all the organization for the conference, which is very well going. Okay, and the second speaker for the tutorial is René Vidal, who is the Penn Integrates Knowledge and Radcliffe University Professor of Electrical and Systems Engineering and Radiology, the Director of the Center for Innovation in Data Engineering and Sciences, and co-chair of Penn AA at the University of Pennsylvania. He's also an Amazon scholar, an affiliated chief scientist at NARS, and a former associate editor-in-chief of TPAMI. His current research focuses on the foundations of deep learning and trustworthy AI and its applications in computer vision and biomedical data science. His lab has made seminal contributions to motion segmentation, action recognition, subspace clustering, matrix factorization, deep learning theory, interpretable AI, and biomedical image analysis. So let's hear from them about the mathematics of continual learning.
Hello. Hello. Thank you, Cyrus, for the introduction. So it might not be a good time because it's now at 11, we have 2 hours. You are supposed to have lunch. But I'm sorry about that. So let's stay hungry, stay continually learning. So let's start. I will begin with a little bit of the complaint as everybody would have. René, can you hear us? Yeah, so I have the habit of keeping forgetting. So say one first question is I forget why I'm even here. Say I have a lot of homework to do as students. I have a paper to write, vacations, it's summer, and I have internship. I'm flying here, and I have an in-house continual learner to train that is called VVN. When we train it in 1.5 months, she begins to know how to sleep. And then in the 2 months, she begins to know how to cry, cry better than before. And then 1.5 months, she begins to know how to be angry. So in the René, so we are synchronizing, okay. So, and then in the, I think 5 months, she begins to know how to crawl and then knows how to sit. So it's like a very good experience of a continual learning. You can see visibly how everything changes every day and even every hour. So I know many of us are coming here, we have a lot of responsibilities, but we still choose to come here for what? So the question is like, why am I even here? I think you have the same complaints, but I think we are driven here for some reason, for one more or less, or in one way or another. We all believe to some extent that continuing learning has a bright future. And in particular, there have been many fantastic talks and many new research directions highlighted throughout the conference, given by the keynotes and the tutorials and the highlight career awards. There are topics like continual agents and foundation models and continual federal learning, and some connections to neuroscience and online learning. Well, everything is like very good, but I have a question that goes backward. I'm not sure whether René has an answer. So the question is, do we also have a bright past? Like we are like a continuing learning, we want to keep not forgetting the past, but do we have a bright past? How do we know that? René, do you have an answer?
Yes, if we think a little bit about what might be the first few references on continual learning, we find these two references that are from 1989 and 1995. And just look at the abstract of the reference on lifelong learning that says that in recent research on learning has predominantly been focused on learning a single task that were studied in isolation. If robots encounter a multitude of control learning tasks over their entire lifetime, then there is an opportunity to transfer knowledge between them. And so if you think about it, a lot of what we study today actually has a long and rich history, and many of these seminal works have to some extent been forgotten. As you can see that the number of citations is not that high. And actually, in particular, you can see that the number of citations has been just growing over the last several years when deep learning became sort of the fashion of the time. What we're trying to do here in this tutorial is to go back in time and to see what was the progression from those original works in the early 90s up until today, and how can we connect modern techniques to techniques that actually existed a long time ago. And even farther, we are going to consider not just 1989, but we are going to argue in this tutorial that there are even very strong connections with the original work that was done in the 1960s. Adaline. Adaline was one of the first algorithms for training the neural networks of the time that primarily consisted of a single perceptron. And at the time, most models were linear. So there is this classical algorithm that we will cover in this tutorial called least mean squares. And the goal, therefore, of the beginning will be to establish a connection between this classical least mean squares algorithm and already the foundations of continual learning. And just to show you a little bit what those connections might be and some early works in that regard, there was this principle of minimal disturbance that was part of this least mean squares algorithm. And if you just read these papers from a long time ago, they say that all this algorithm, Adaline, relies on the principle of minimal disturbance, where the idea is adapt to reduce the output error for the current training pattern with minimal disturbance to responses already learned. And you just read this very old paper and you immediately connect to the question of training on your current task while trying to not forget about what's already been learned. And in this old work, this principle of minimal disturbance is also defined with the idea of that during training, it's advisable to inject new information into a network in a manner that disturbs stored information to the smallest extent possible. So you already see even the roots of online learning with memory, in the sense of storing some information from the past in order to be able to inform future learning. So the issue was that if we look at the 1960s, this Adaline algorithm was not gradient based. So this was before backpropagation was invented in the 1970s, 1980s. And there was already a lot of talk back then about the question of whether this LMS algorithm that was designed primarily for linear networks could be extended to multi-layer networks. And that problem at that time was considered as a difficult problem. As reported here, you can see then that because of this difficulty, work switched from least mean squares to what was then known as adaptive filtering, and that led to the growth of a field that developed over the next 30 years or so called adaptive signal processing, which was one of the cornerstones of signal processing in the electrical engineering community. So one example of those adaptive algorithms is the affine projection algorithm that we're also going to cover in this tutorial. And this affine projection algorithm was introduced in 1975. And well, the original reference, as you can see here, is in Japanese. So I apologize, I can't read Japanese to you. So I'll read a little bit of the 1984 version here that essentially speaks to this challenge about the LMS algorithm and how to extend it in an adaptive way. So it says the LMS algorithm and learning identification, which are typical adaptive algorithms, have a problem in that their speed of convergence may decrease greatly depending on the property of the input signal. To avoid this problem, this paper presents a geometrical discussion as to the origin of that defect and proposes a new adaptive algorithm based on the result of the investigation. So you already see that geometry was becoming essential in adapting these algorithms. And that's exactly what we're going to be talking about today. So the adaptive filtering literature went into multiple directions, all of them somehow connected to, or we will be able to connect them to lifelong learning today. And already in early 1975, it was acknowledged that this area of research became really very robust and important. So for the purpose of this tutorial, it builds on a series of books and papers that have been written throughout the years. In particular, we will begin, as you see on the top left, with the Adaline algorithm and its connection to least mean squares. We'll continue with the question of catastrophic forgetting with shallow networks and show how that can be addressed via the affine projection algorithm that I just mentioned. We'll then move forward to the deep learning era of lifelong learning and show some connections with some adaptive algorithms such as recursive least squares. And we'll end the tutorial with deep continual learning and how that connects, or some aspects of it at least connect with very old techniques also from signal processing and controls, such as the Kalman filter. The question is, how are we going to do that? Because on the one end, modern continual learning applies to nonlinear models and deep networks. It's able to capture arbitrary data distributions. And by and large, training these complex models on arbitrary data requires solving non-convex optimization problems. On the other end, these classical techniques, such as least mean squares and adaptive filtering and so forth, have typically just considered linear models, and they also have autoregressive models in mind. And typically, the types of losses that are considered are square losses. So you typically, therefore, have quadratic objectives, which when combined with linear models leads to convex problems being solved. So naturally, there's going to be a big gap in principle between continual learning and adaptive filtering. And so we will try to bridge this gap by beginning with these linear models and extending them to arbitrary data, and beginning to highlight how these classical algorithms naturally extend to some classes of deep networks and nonlinear models throughout the tutorial. So to summarize what's coming, I'll begin in part 1 of this tutorial with a description of least mean squares from the 1960s and show how that connects to the problem of continual linear regression. Then Liangzu will move into part 2, where he will talk about the affine projection algorithm and show how it connects to a modern continual learning algorithm called gradient projection. And the extension between parts 1 and 2 would be to add memory to the continual learning algorithms. We'll then move into part 3, where Liangzu will cover the least recursive least squares algorithm and show how, by using basic algebra, it can be connected to some of the network expansion-based algorithms for continual learning. And here, the key extra insight relative to the affine projection algorithm will be the addition of noise. And finally, Liangzu will conclude with a discussion of the Kalman filter and establish connection with modern notions of in continual learning, such as positive backward transfer. And this would be done by adding task transfer to the picture. All right, so with that in mind, and before part 1, let me get started with some basic definitions and notations that we are going to be using throughout this tutorial. So we will begin by considering a simple linear model. So in this particular case, let's say I have data X, I have a true model theta star, and I'm trying to predict a variable Y, which is in this case scalar valued. We'll consider the vector valued in a moment. So let's assume that we get one sample at a time. This will be denoted here by X sub t and Y sub t. For technical reasons, we'll assume that the data is on the sphere, so this is unit norm. And notice also that I've put here within parentheses that we can also be representing one sample per task. The idea here would be that a very trivial online learning setting will be one where at every time instance, we're simply given a new data point, but this new data point now corresponds to a different task. So we'll be distinguishing those cases in a moment, but we can consider this as I just have a single task and I'm just given the data incrementally, one data point at a time, or we have multiple tasks and at every point in time we're given only one data point. And so the goal of continual learning typically is that I'm given a new task, or in this case, just a new data point, and I already have some estimate of the parameter theta at step t minus 1. And what I would like to do is to update theta t minus 1 to theta t by considering the new information in the pair x sub t, y sub t. Okay. Last piece of notation here, we would also consider matrices, capital X sub t here as the set of all inputs from x1 through xt, and likewise the vector y sub t will represent here the set of all outputs from y1 to y sub t. Okay, so beyond defining what the model and the data and the parameters are, it's important to also measure how well we are doing. And so we are going to consider this matrix of residual errors, where epsilon ij represents the error task I when we have model j. And this is represented here by theta j. And so in thinking about this matrix of errors, we can split it into multiple parts of it, this red region, this blue region, this purple region there. So what are these different kinds of errors that we can consider? So the blue part pertains what is the error in the current task with the current model. So this means, we are receiving this data sequentially and we are updating the models as we go along. And so at the last step, we fine-tune our model with the current task and we can measure the error in the current task. And so this is what the diagonal aspects of this error matrix are going to denote. At the other end, at the top, what we have is, well, once we have a new model, we can look back and see, well, how good is this new model on previous tasks that from which we had already learned in the past. And ideally, what we would like for a good continual learning model is that it does as well as the previous models in the previous task as well. If it doesn't do as well, if these errors sort of increase, then we have what we know as the catastrophic forgetting problem, where we are now doing better on the new task that we have just learned, but we begin to do badly on previous tasks that we have already learned. And so controlling these red errors is also an important part of the continual learning problem. And naturally then, the errors for the future tasks, given our current or past models, is what this other region. And of course, there is a lot of work on online learning theory trying to address these aspects. So for the purpose of this presentation, we're going to be focusing on the current and past, and so all of the red area and blue. And so the goal will be essentially, how do we update the parameters of this linear model from t-1 to t, while guaranteeing that we have small errors on the tasks that we have already seen. Okay. So to do that, we're going to have some measures of those errors. So one of them is the so-called mean squared error, where, as illustrated here, say you take the last column of the matrix of errors and you simply take the sum of the squares of the errors so far. So in other words, what is the mean square error at task T? What that means is that we take the model that we have just learned for task T, and we look at what errors does model T make on all previous tasks 1, 2, 3, up to t-1, including T. And we compute the average of the sum of the squares of errors and divide it by T. And so that's where we're going to denote by the mean square error. Another measure that we will use is the measure called forgetting. And in this particular case, what we do is that we look at the error for task I that is made by model T, and we compare it with the error that model I made on task I in a few tasks ago. And we measure the difference between those two. So this is sort of the relative change of the error. And naturally, we expect that when we learn a new task, if there is catastrophic forgetting, we're going to have a new error that is higher than the previous error. And so if the errors are the same, then this measure would be 0 and then would be therefore 0 forgetting. Now, in practice, what we can observe is that the mean square error is bounded above by forgetting. And with the advent of over-parameterized models in particular, we can get the error at model I trained on the data I to be relatively small, if not 0. And so because of that, throughout the tutorial, we'll primarily concentrate on the mean square error, but it's important to have in mind how that relates automatically to forgetting, particularly in the case where epsilon II is 0 or very small. Okay, so with that in mind, let me now finally get started with part 1 that will relate least mean squares from the 1960s to continual regression. So we'll begin with the formulation at the very top, which is just a classical linear regression problem. So x of I and y of I denote the data, input and output, and theta denotes here the parameter, and we're trying to find the parameter that minimizes the sum of the squares of the errors. We try to do that using, say, the gradient descent algorithm, where the new parameter theta t is equal to the previous parameter theta t minus 1 minus gamma times the gradient. Gamma here is the learning rate or the step size of gradient descent. And what we have here is simply the gradient of the objective at the very top. Now, here there is no continual learning yet. This is just simply I define a linear regression problem and I want to solve with gradient descent. Obviously, this appears a little bit silly since for a linear regression problem, we know how to compute solutions in closed form. So why would we do gradient descent? It's a little bit silly at the moment. But nonetheless, the reason for doing so is to begin to establish that connection with continual learning. And so the way to begin to establish that connection is by considering a stochastic gradient descent version, where instead of minimizing the sum of the squares of the errors, we are minimizing the expected value of the squared error as illustrated here. And so if we consider the stochastic gradient of that expected value of the square error, we are going to get exactly one term of the sum. And we can choose. So in particular, if we choose the one term, in this particular case, the index I, if we choose it to be t, that's exactly when we're going to get the MLS algorithms, as I'll describe in the next slide. But in here, all I'm saying is if we consider the objective at the top, which is linear regression, and we apply stochastic gradient descent to this linear regression problem, we're going to get this update equation that you're seeing right there. And in this update equation, because we are using stochastic gradient descent, we are supposed to choose the data point xi, yi at random from the n data points that are given. So this choice is at this point not sequential, but rather random. So it is only once we impose that we're going to make this sequential that we get the LMS algorithm. And so the LMS algorithm is written here. And as you can see, the main assumption is that we don't have all endpoints from the beginning. And rather than choosing at random one of the n data points, we're just going to choose the only data point we have, or the most recent one, which is xtyt. Okay? And so the interesting observation about this algorithm is that even though it is, as I just mentioned, strongly connected with stochastic gradient descent for linear regression, we can think of it as trying to solve a continual learning problem. How? Well, in this objective, we have the minimization of theta minus theta t minus 1. So this objective simply says you're given an estimate of theta thus far, and you want to find a new estimate, theta, that is close to it. That's all what it says. Subject to what constraint here? Well, if we think of the first term, this is the new error. I'd like the new error to be related to the previous error. And I'd like that relationship to be characterized by this 1 minus gamma factor. So in other words, what this is trying to say is find a new parameter theta that is close to the previous parameter theta t minus 1 so that I preserve the knowledge as encoded by theta. But I am trying to reduce the error because the new error after the theta is going to be equal to the previous error times some factor. And if that factor is less than 1, then we're going to be reducing the error. And so this is sort of a continual learning setting in that I have now a sequence of tasks and a sequence of parameters, and I have certain error, and I'm trying to make that error smaller and smaller by a certain factor, in this case 1 minus gamma, while at the same time preserving past knowledge by not deviating too much from the previous theta. And it can be shown that this the updates are absolutely equivalent. And so whether we are solving the original least squares problem via gradient descent, or whether we are solving this continual learning problem, the update equations are the same. So in fact, this is exactly what I was mentioning in the introduction. This is exactly the minimal disturbance principle. And in fact, as you can see from this quote of this paper from 1960s, the LMS algorithm had existed for several months as an error reduction rule before it was discovered that the algorithm uses an instantaneous gradient to follow the path of steepest descent. So what I'm trying to say here with this quote is simply that even though I began with least squares and then tried to adapt it, the reality is that it was a little bit the other way around. Okay, so is there any theoretical result for the LMS algorithm? And the answer is clearly yes. So what you can see at the top is, again, just a restatement of the update equation of the LMS algorithm. What you see in the second equation is simply a reminder of what the error was, which is the mean square error, the sum of the squares of the error from task 1 to task t. And notice, and so the main theorem says the following. If the data x1 through xt are drawn IID from the unit sphere, then the expected mean square error is bounded above by some rate that I'm going to describe in a moment, raised to the t power, times the initial error of the parameter estimate. And so what you can see here is the following, that the rate is determined by gamma, which is the step size, and by the smallest eigenvalue of the covariance of the data. And so this gives you, in fact, a exponential decay, and therefore this proves that the least mean squares algorithm converges exponentially to the true solution theta star, starting from any initialization, as long as you select the step size gamma in a suitable manner that depends also on the minimum eigenvalue of the covariance of the data. In the next slides, I'm sorry for that, and I'm going to bore you with the proof of this. It's just because the proof is relatively simple, but there are a few ingredients of that proof that will be useful for the statement of the results later. So I apologize for going through the proof, but it should be fairly simple, so don't worry too much about it. So here's how the proof goes. We begin at the top right with just the update equation, which is just what defines the LMS iterate to begin with. The first thing we do is relatively straightforward. So we are going to subtract theta star from the left and from the right, from both sides. And immediately we're going to get here, as you can see, the error at iteration t. And here we now get the error at iteration t minus 1. What we're also going to do is that we are going to substitute y sub t by what y sub t is, which in this particular case is just the dot product between xt and theta star. Okay, so this is just a substitution of what yt is. So that's the first step. So fairly trivial, just subtract theta star. The second one is just rearrange the terms, and we are going to utilize the errors. So the errors are going to be here zt, which is theta t minus theta star. So this is the error in the parameters. And so once we do that, we get immediately that the new error zt is equal to the old error zt minus 1. But there is going to be some matrix multiplication in the middle, and this matrix is the identity minus gamma xt transpose. And that equation is the one that's going to be critical both for a single task and a single update, or in the case of multiple tasks, as we'll see in a moment. And I want to spend a little time explaining what this update means, because it's going to be relevant. And in particular, what is the influence of the step size? So if gamma is chosen to be 0, then we do nothing. The new ZT is the same as the ZT minus 1. So we don't reduce the error at all. If gamma is equal to 1, then we get here identity minus xt transpose. And because xt is unit norm, which was one of the assumptions, this is simply a projection matrix. So in other words, we take the error at iteration t minus 1 and we project it. We project it along the orthogonal complement to xt. And so this is what's illustrated here, that if we select gamma to be 1, we're just going to project it onto this subspace here. At the other end, if we choose gamma to be equal to 2, then we are going to do a reflection. That is, ZT minus 1 is going to move to the other side of the subspace orthogonal to xt, and it's going to be sort of the reflection relative to that subspace. And so you can see here, therefore, that the selection of the step size is going to play an important role as to whether we do nothing or not move too much, or whether we project onto a subspace, or whether we reflect the data point all the way to the other subspace. Okay, so step 1 was simply subtract. Step 2, we rearrange a few things, and we got this update equation that relates the error at time t versus the error at time t minus 1. So what do we do next? So what we care about is this mean squared error, which is the sum of the squares of the errors from either task 1 to task t. And this equation here is using a simple inequality to simply say that this error is bounded above by the norm of this parameter error vector zt, okay? And this inequality comes simply from the fact that these are all unit norm vectors. And so the sum of the squares of the xi's is equal to t. In this particular case, so the t cancels. So with that in mind, all we need to figure out in order to derive this convergence rate is what is this zt, what is its norm, and in particular, what is the expected value of its norm, and whether we can bound it above in order to get a bound for the mean squared error. And so that's indeed the case. So if we take the expected value of the norm of zt squared, just by using the recursion that we already have, we know that this is going to be related to a quadratic on zt minus 1. And the quadratic is going to have this matrix, identity minus gamma xt transpose squared in the middle. And that matrix is effectively going to give, if you do the calculations, because of the unit norm assumption as well, the equation that's written here. So identity minus gamma times 2 minus gamma times the expected value of xt transpose. And with that in mind, we have now zt minus 1 transpose times this matrix times zt minus 1. So that's a quadratic. And so that quadratic is bounded above by the maximum eigenvalue of the matrix. And the maximum eigenvalue of the matrix is given here. So the largest eigenvalue is going to be 1 minus gamma times 2 minus gamma times the smallest eigenvalue of this covariance matrix. And that's exactly how we get now the rate, because we are done. On the left-hand side, we have the expected value of zt squared. On the right-hand side now, we have the expected value of zt minus 1. And we have the bound in the middle. So if we just do unrolling, we're going to get that this is the rate to the t times the initial error as we expected. And so that completes the proof. So it was hopefully short, just a page or so. But the main point again is to repeat that we get a bound on the mean square error. And that bound is dependent on the step size gamma and the smallest eigenvalue of the covariance matrix. And therefore, if we choose both of them carefully, we can get an exponential rate of convergence for this mean squared error. Okay, so good. This is good. This means that if I'm just solving a linear regression problem, I can have exponential convergence. But there are some strong assumptions here. And one of them is that these x's, x1 through xt, are IID samples. Is that a strong assumption? Maybe for linear regression, maybe that's okay. But if we really consider this as a continual learning problem, and if we think of x1, x2, x3, and so on and so forth as samples from different tasks, then we might not be sure that these are IID samples. Maybe there is some relationship between the tasks that we need to consider. And so the question is, what do we do when these samples are really drawn from a sequence of tasks? And so one assumption now, fast forward almost 70 years from that old 1960s paper, one assumption that theoretical papers in continual learning have been doing recently in order to bound this mean square error is that, if the data is coming one data point at a time, you cannot expect to learn them all, right? There needs to be some relationship among the tasks that allows you to learn, because it cannot be the case that any point is from a completely new task, and if there is no relationship among the tasks, obviously you cannot learn. So one assumption that is typically done is that there is a finite number of tasks, in this case, P of them, and that they are recurring. So you do task 1, 2, 3, 4, P, and then you repeat again. So therefore, the data at task T plus P is the same as the data at task T. Okay, so can the classical theory for MLS and the convergence of it be extended to these cases where we have P recurrent tasks? So here's one case that was recently studied in 2022, where this is the case for what is known as two recurring tasks. So it's just two tasks, and we are going to have task 1, task 2, task 1, task 2, and so on and so forth. And in this particular case, as stated in the theorem above, it says that if you apply the LMS algorithm with a step size gamma that is equal to 1, and you consider now the error after 2t steps, then that error is bounded above again by the initial error z0 squared with a rate c. And this rate c is nothing but the dot product between data from the first task and data from the second task. So geometrically, if these tasks were data from a subspace, this is sort of related to the angle between the two subspaces. And in fact, to understand just, this is not, I'm not going to do more proofs anymore. This is just a very intuitive geometric picture trying to convince you why you might get convergence and what's really going on. Well, what you can see here is written in the remark in the box. So what is the relationship? So as we've already seen from the proof of the classical result, we begin with some error z, and then we need to project it orthogonal to the task 1, which is x1 here, and that's the identity minus x1 transport. And now we need to project it again via task 2. And because the tasks are alternating, then this algorithm is just doing alternating projection. So you project onto the orthogonal complement of task 1, and then onto the orthogonal complement of task 2, and then you go on. And so this is illustrated with a figure here. We begin with some error at iteration t minus 1. We project it onto the orthogonal complement of task 1, and then we project it onto the orthogonal complement of task 2. And you can immediately see that if we keep doing the projections, right, we begin here, we go down, we go up, we go down, eventually we expect to converge to the intersection of these two subspaces, and a parameter vector theta that is at the intersection of these two subspaces effectively solving both tasks at the same time. And what this algorithm will therefore do is to produce a sequence of alternating projections that will be provably convergent to a vector theta that solve both tasks. All right. And can we extend this to more general settings? So there is this other paper here, 2024, where the setting is extended in a way that you can actually achieve zero error in a finite number of steps. How can you possibly achieve that? You can achieve that because instead of choosing a constant step size of 1, you can choose a variable or adaptive step size. And in particular, the selection of the step size here is equal to 1 if the task index is odd, and is equal to 1 over 1 minus c if the task index is even. And so c here is again the dot product between data from two different tasks. And so why does this happen? Why is it possible to converge in only 3 steps? And again, you can see that here, that what's going to happen is that we're going to begin with an initial error z0 inside this remark. We project orthogonal to the first task, and then we do this different projection. It's not quite a projection because gamma 2 is not equal to 1. And that projection effectively does something like a reflection, and we can see this here. So if we begin with z0, the first step will be to project onto the orthogonal complement to x1. So we arrive at this point z1 here. But then in the second step, we are going to move orthogonal to the orthogonal complement of x2. But we're going to choose a step size where we go, if we go farther, then eventually we want to arrive at a point z2 such that when projected to the orthogonal complement of x1 again, we are already at the intersection. And so that means that in just 3 steps, we can get there without having to iterate by orthogonal projection every time. Okay. All right, so all this seems sort of relatively simple linear problems. Can this be extended farther? And so it turns out that there are connections also between least mean squares and very modern techniques that are the core of large language models, which is simple or maybe simplified versions of the well-known and well-established attention mechanism. So let me go through that. First, let's begin with a vector extension of least mean squares. So here we want to minimize the expected squared error between theta. Now is not a single parameter vector, but it's rather a matrix. And so theta times x is my linear model. Y is going to be the vector that I'm trying to predict, and is not a scalar anymore. And let's, as before, use stochastic gradient descent, and let's use just with the data arriving one at a time, and we can derive the update rule that emerges from stochastic gradient descent with a step size of gamma is equal to 1. So as you can see, it's nearly identical to the LMS rule we had before, except that now we have this outer product of the y, which is a vector, and x transpose, which is also a vector. So theta is now a matrix. That's the main thing. But as you can see, the new theta is really equal to the old theta projection on the right onto the orthogonal complement of xt, and then we have this extra term in that here. Okay, so we are going to try to relate that to the attention mechanism. So you should all be familiar with the attention mechanism, but if you're not, the idea is that you produce some output denoted here by O sub t, and that output is a linear combination of vectors v sub t that are typically called values, and the vectors are weighted by some coefficients c sub t here. And these C sub t are the attention coefficients. So what are the attention coefficients and how are they typically computed? So the attention coefficient C sub I here is nothing but a softmax applied to the dot product between a vector K sub I, which is typically known as the key, and a vector Q sub t, typically known as the query. All right, so in other words, we compute dot product between keys and queries, and then we apply this softmax expression that gives us coefficients that are between 0 and 1. And so going back to the output O sub t, this is nothing but a linear combination of the values V sub t's with coefficients that are between 0 and 1. And these coefficients, furthermore, add up to 1. So this is an affine combination of the values. So we're going to do we're going to be using here a slightly different attention mechanism that is typically called linear attention, which is the same as what I just said, except that there is no softmax operation. So the coefficients are given directly by the dot products between keys and queries. Okay, so how does this simple linear attention mechanism relate to the LMS algorithm? So the relationship is that if we look at the updates that are being done by the LMS algorithm and the relationship between theta t and theta t minus 1, and if we think of the output as the values and the input data as the keys, and therefore the yt xt transpose is replaced by vt kt transpose, then what we're going to get is that the following. If O sub t at the bottom is obtained by taking the theta t matrix and multiplying by the query qt, we're going to get identically the same output as linear attention, because if you solve this linear RNN recursion here, then the solution to this is given by the sum of vt kt transpose. So once you multiply by qt, you're going to get exactly the sum of ci's vi's. All right, but that's almost there. Not quite a one-to-one correspondence yet, because we have this orthogonal projection. So what do we do about it? What is the main issue? So indeed, the main issue is that if we just do this recursion as is, we might have a situation where the parameters theta keep growing. And that's exactly what was avoided by using the softmax attention, where the coefficients were restricted to be between 0 and 1. And now if you use just linear attention, then these coefficients are not guaranteed to be bounded. So that's exactly where adding this extra projection onto the orthogonal complement of the xt's that are now reinterpreted as keys, that's the job of avoiding that this recursion grows unbound. So in summary, the way to relate the LMS to the basic attention mechanism is to consider the input data xt as the keys, the output data yt as the values, and then consider the query qt as the input to the linear system here defined by the parameter theta. All right, so that is the conclusion to the first part of the tutorial. I think the main points that I've tried to make is that continual learning has a very long and rich history, and we argue here that it all begins with a method that was developed in the 1960s that is called least mean squares, and it was developed in conjunction with the Adeline algorithm for training neural networks. The theory for LMS to reduce forgetting requires revisiting past tasks, or alternatively, we can consider that this is just least squares with a linear model, so it's just a single task and we're just getting new data for it. And a core motivation for modern continual learning is that SGD forgets catastrophically for deep networks. So there is still a gap between these linear models and deep networks. So in what follows, Liangzu is going to present extensions of this basic LMS method that will address the question of forgetting and trying to extend it also to non-linear models.
I'm sharing a wrong screen, sorry. I don't know. Okay, maybe I need to move it. I'll move it two screens. Maybe it is my problem. Okay, I see it. It's my problem. It works now, okay. Okay, thank you very much, René, for the introduction of the LMS algorithm. The subsequent algorithm that we are going to introduce they can all apply to this attention mechanism as well, but we are not going to do that. We are going to talk about more connections to continual learning. The algorithm we're going to talk about now is called a fine projection algorithm. And for this, let's better introduce it by making a comparison to least mean squares. So the comparison is this. Least mean squares, as we interpreted it, is like a constraint optimization based method. And then the constraint is like this. If you set gamma equal to 1, and then you would have exact constraint, yt is equal to xt times theta. And the APA can be viewed as an extension of LMS in the sense that it now employs a sliding window of memories that is of size B. The sliding window is the most B recent samples. You have this memory stored. And then you put more constraints. Your constraints is to say that your B most recent samples should be explained well by your model theta. And therefore, like by this construction, you would expect that it works better in the sense that you have more data on the constraints, you forget less, and you forget less about the recent, but you don't have remote past, the samples of the remote past. And in particular, because you store data, you can naturally view this as a replay-based method. And in particular, in adaptive filtering, they are called data reusing family. They don't call it data replay, but they call it data reusing family. Okay, but the issue, not the issue, but the point of this approach is that it's a little bit difficult to get strong non-forgetting guarantees because it depends on your window size, B. If you store no sample, you get the same guarantee as LMS, but you store like B samples, your different updates will have some correlation because they would depend on your past samples in a non-trivial way. But what we can do to have a good guarantee is that we consider, like in the ideal case, the simplified case, that we have a perfect memory. We simply store everything. So now the constraints is that we require all the data are fitted perfectly by your model. And this avoids forgetting by design. And the most important thing is that we will show this naturally connects to many, many continual learning methods. So what we are going to do next is to show this connection. The first step that we are going to prove is that even though we have this perfect memory formulation, APA star, you have just constraints saying that you are not forgetting. And you have the objective saying that you are going to be close, stay close to your last estimate. And we will show that this theta t-1 can be replaced by theta 0. We will show that. And the next step is to show the equivalence between the minimum norm solution and a paper called a method called ICL, ideal continual learning. It's not in context learning, but it's called ICL as well. This requires your initialization to be 0, but then by solving the ICL program, you get an exactly equivalent solution as the minimum norm solution. And here in ICL, the deal is that in the constraints, you enforce the past needs to be remembered. And in your objective, you minimize your current loss. So by separating your constraints, but your data in this way, you can better you can basically enforce that my past needs to be remembered. I don't care how well the current is optimized, but my past has to be remembered. And then we will show the equivalence between the algorithm called orthogonal gradient descent that is more famous, and the other one called OR fit that is for subsequent improvements. In this step, we will show that by solving ICL in a particular way, we get this update rule. And here, P is a projection onto the orthogonal space that is orthogonal to all previous samples. Because like you see in LMS, we project onto the orthogonal space that is orthogonal only to the current sample. But here, we project it onto the space orthogonal to all samples. That's the main difference. And because of this projection, now the algorithm has the name orthogonal in it. And finally, we're going to show how to apply all these equivalent methods now to the so-called deep networks. Is now that gives us the method gradient projection. So it is widely known that gradient projection was proposed by paper 4 and 5, nearly concurrently. But the history is a little bit more convolved. We will talk about it more in the third part. So let's begin with the first equivalence that we're going to prove. And we are not going to do the full proof, but we are going to begin with the basic geometric property about solving least squares problems. This is basically a minimum norm problem starting at point Q. And this program says that we're going to project my point Q onto the affine space defined by these affine equations. So, and then this is equivalent to project, because we have affine equations. If you take a difference with the feasible point, you get somehow, you make the equations linear. Therefore, this projection is a linear projection. And this is somehow a reinterpretation of this, but you can take any feasible point. This is an algebraic problem rather than optimization problem, so it will help us to make a proof. In particular, if we say we're going to look at the minimum norm solution, we define this difference, and we choose this feasible point theta star. And then we will get, by solving this minimum norm solution, we know that this solution has to be a projection of Z0, because your objective, you start with theta 0, you do a projection. And similarly, if you do APA, what you're going to do is you solve this program for all t from 1, 2, 3, and up to all t. And by doing this, you're accumulating all the projections. So you start with Z0 at time 1, and then project by P1, and then project by P2, project by P3. But it is important to notice that this sequence of projections, they are content, they project onto a subspace that is orthogonal to your data, but you're accumulating your data. So you are reducing the size of your projected dimension. So basically what this means is that, okay, here, in minimum norm solution, you are going to do a direct projection onto the smallest subspace, because when you have all data, you look at the orthogonal space that is the smallest. But at time 1, you have only one data point. The orthogonal space has co-dimension 1. That is dimension d minus 1, because you have only one point. And therefore, this sequence projection, what you are doing is going to project sequentially onto a smaller and smaller subspaces. This is shown in the figure. Like if you do sequential projection, first of all, you can do Z0 here. You project onto the span of your first data sample. And the next point, you project onto the span of 2 previous samples. So that is the intersection of this line. But instead, if you do a minimum norm solution, you will just do this projection directly. And by this geometry, you will simply get these 2 points. You arrive at the same points. So this is a geometric interpretation rather than a proof. Oh, now let's move to step 2. And again, we are basically using this geometrical property again. So what we're going to do is this. We set in this equation, in this property, we set Q equal to 0, meaning that we project starting from initialization 0. And we take the theta t. Theta t is the point where that has a minimum normal solution. That is a feasible point of ICL. And therefore we get this condition if we want to show ICL produce a solution that is equivalent to the minimum norm solution. We are going to prove this equation. But because basically this projection is 1 minus PT that is project onto the data space. In other words, we are going to prove that after projection, your point doesn't change because theta t, what we can prove is like theta t is equal in this space. So that's what we're gonna do. And we are going to do an induction. For the base case is very simple. If t equal to 1, we have no constraints. We just have the objective. This has one sample, and you can solve it in closed form. That it gives you theta 1. By inspection, you will see theta 1 equal to y1 times x1 is a solution to this problem. And then you naturally see that theta 1 is in the span of x1 because it's just x1 times y1. And we then have some kind of inductive hypothesis. We're going to consider t larger than 1. And because you have this affine constraint, all the solutions can be written as a affine combination of your particular solution theta t minus 1 plus a projection of any point. This is then we can substitute this form of solution into the objective. We basically kill the constraints. We get an unconstrained problem. And here the thing is I write it in a way that it is very similar to our previous problem, because if you rewrite it, you get yxt transpose times pt minus 1, that is your projected data. And yt minus xt transpose theta t minus 1, that is your remaining residue. So they are denoted by xt bar, yt bar respectively. And you get a similar problem as before, as in the case of t minus 1, t equal to 1. And you, by inspection, you have a solution already. You know optimal solution is A equal to xt bar times yt bar. But we are going to go back to the original space to rewrite it. So of course you need to normalize it, sorry. And then you get this. These are just like a little bit of algebraic calculation. You substitute the definition of xt bar, yt bar here, and then rearrange a little bit of the things. Because what we are going to prove is that theta is in the span of the data. And we are going to see that very easily based on this equation. Because by inductive hypothesis, theta t minus 1 is in the span. And xt is in the span because this matrix contains xt already. And this projection will bring your data into this span because pt minus 1 is a projection onto the orthogonal part of the data. And you have one I minus of this. I is the identity matrix. So basically we have proved this equivalence. But now, how to see the connection between OGD or OR fit? Actually, we have seen that already. The reason is that we have derived the update formula for ICL, and this would give you the same form of this. You will see. If you observe these two equations, they're almost the same. The only thing is that in OR fit, the authors have chosen the step size gamma t is equal to 1 divided by this inner product in the norm pt minus 1. And if you have this choice of step size, you then observe this equation is identical to that equation. But OGD doesn't specify the step size because it was like a proposed for nonlinear models or deep networks. So it's very difficult to choose a optimal step size. So given this equivalence, we now see all these methods are actually to some extent equivalent. So we will do a little bit of some math on how to updating this projection matrix, which will be very important in what follows. So by definition, this projection is to project onto a space orthogonal to data. So then if we have a UT that is an orthogonal basis of the data, we simply have this relation PT is equal to identity minus the projection onto your data, that is UT times UT transpose. And then what we can do then is instead of updating PT, we can update it by update UT by Gram-Smith orthogonalization. This method is going to be like, for example, t equal to 0, we set UT is equal to 0, we have no points, and the projection is the identity matrix, P0. And then if t is larger than 1, we are going to do Gram-Smith orthogonalization by just attaching a new row to UT minus 1. This new column. This new column is normalized because we need a orthonormal basis, and it is projected the previous point that we see. That is a projected data point. And this algorithm is to be familiar, hopefully. But there is a more interesting thing that we want to show. That is how to directly update PT, because it gives you how. In this case, you don't need to construct UT, right? So. And then what we do is just by following the definition. PT is equal to the orthogonal complement of UT, and then you get the first equation. Second equation, you use the definition of UT because the UT transpose is equal to UT minus 1, UT minus 1 transpose, plus this term. This term is basically somehow the out product of the new column. And you get an update formula that is your new projection is equal to your previous projection minus some out product of the projected points, because PT minus 1 times XT is your project points. That is out product divided by inner product. This inner product is measured by this projection. And we will see that very often like in subsequent development. So it's very important to remember it like this is outer product divided by inner product. So, and then we're going to see how all this can be expanded for deep networks in a layer-wise way. So I'll just give you some basic definition of deep networks. I hope this is very familiar. Okay, so the way that we define it is kind of a recursive. We start with your original feature X, and then we define your network to be F theta of 0 of X is equal to your original data. And we do a linear layer, I would say maybe, a linear layer. So this is a linear layer, I assume, recursively, but parameterized by theta, capital theta. And then we do a nonlinear activation, sigma. And I define this output of the nonlinear activation to be, I just call it output features of layer L. Actually, at each layer, you have input features, but it's a little bit more difficult to manipulate input features because I would have another index L-1, so I don't define it. I'll just call it output feature of L. So this is output feature. Your input X is your output feature of layer 0. And our goal is to update our network given an input XT and a label YT and a loss. And then by this, we can draw a very nice analogy for the deep network case and the linear case. Here is now familiar because we are now doing a projection. We have been done a projection in a linear layer that is just to project onto the space orthogonal to your input features. That is the output feature of layer L, layer 0. And the generalization is quite straightforward, but even though the notation is a little bit ugly. So PTL is just the projection onto the subspace orthogonal to output features of layer L. Here is layer 0, and that is layer L. Yeah, stacking all the linear layers together. So let's proceed by looking at the update rules. On the right-hand side, we see the update rules for the linear layer. We simply have some step size. The update direction is the step size times the projection times some stochastic gradient at time t. But in a gradient projection for deep networks, you do the same basically. It is only that you have you do this for every layer first, and then the update direction is the projection of the layer times your update direction, your original update direction. That could be stochastic gradient, could be your item update direction. So this is like a quite direct generalization to the layer-wise case. So the point of this generalization is that you have a very nice result that given once you learn the xi at the task I on the right side here, you go through the subsequent tasks, and when you learn the subsequent task t, the output of this won't change. So this is like the output features will be invariant starting from that point you receive xi. So I think this is illustrated in this figure by saying that once you receive x1, you update theta 1. And from that point, you get all blue. That means that the feature doesn't change. You have all these equations. And similarly, at the point where you receive x2, you get all purple. You have the same values of your output feature. And for x3, you have all red, starting from task 3. And here, I think I'm going to skip the proof because there are a lot of notations. But I think the basic idea is just to say that, okay, you have a layer-wise application of this projection. And you do, so the proof goes like at the first layer, you have the same property as a linear case. And then you get the output. At the second layer, you get the same output. And you get a similar property. And you just proceed like in this way. I think I need to go faster. Okay. Hopefully now at least get that. I give you a lot of slides in light of time. I hope now you get at least some feeling about everything here. You basically have some classic algorithms, and then these are connected to recent algorithms, but moreover, it is applicable to deep networks. But the thing is, here, this advantage is that you basically have a noiseless data. Because you are doing geometric projection, if your data is not exact, your constraint won't be feasible. You have a lot of constraints here, and then all these guarantees won't be applicable. So the next paradigm that we're going to introduce is how this recursively squares approach addresses the case of noise. In particular, it has a nice connection with the network expansion methods, and also it generalizes the gradient projection method. That one is based on some low rank update. Now, similarly, we can see some analogy of this RS objective and the previous one. Previous one, we have our current objective constrained to your previous objectives. But now in RS, what you're going to do is very simple. I'm just going to solve a least squares problem. You have a least squares term, summed over all your past samples. And you have a regularization term that is lambda times your some weight decay. And this is more similar to ridge regression, but the only difference is that you have something called a forgetting factor that is between 0 and 1. This, you can see that is divided by beta I. So if I increases, meaning that my task index is larger for most recent tasks, this beta to the power of I is going to be smaller because beta is between 0 and 1. Therefore, this division is going to be larger. And therefore, for most recent tasks, you put larger weights. For the far remote past, you put smaller weights. And therefore, essentially, you can then gradually downweight your previous samples and gradually forget the past. This is somehow, you can call it fading memory because you are fading away from the previous samples. So we're going to show even their formulations look a little bit different. Their update rule would be equivalent as soon as beta is going to 0. The key thing about the RS is that you need to define this regularized covariance. Basically, you have the covariance of basically X times X transpose. That is the classical covariance. But because you have divided by this forgetting factor, you have a BT inverse here. This is BT is basically the diagonal of beta squared up to beta to the power of T. And then you add up this lambda there, regularized. This is, you can then, if you take the second order derivative of this objective, you simply get the Hessian of the IRS objective. So you can also think of it as your Hessian matrix. And then what we care actually is the inverse of this Hessian, or the inverse of this regularized covariance. And why this is important? Because we now basically have, if you take the second order derivative, we get a theta t is equal to the inverse of the regularization covariance times the covariance between your label and your data point. So we have two covariance metrics here. One is the covariance between your label and data. The other is the covariance between among your data, but inversed. So, and therefore, in order to compute a solution of RS, what we're going to do is just continually update the inverse of the covariance, because this part is very easy, very trivial. You can just update it very easily. So we're going to omit some details, but the point is the original regularized covariance, they are updating according to a rank 1 correction. So basically you have the original inverse. Your new inverse, your new covariance is going to be the rank 1 update of your of the covariance. And therefore, I'm forgetting how this formula goes, but if you apply this Sherman-Morrison formula, you're going to get the update rule for the inverse of the covariance. And so now notice that previously you add a rank 1 matrix. Now in your update of the inverse of the covariance, you're going to minus a rank 1 matrix. So the beautiful analogy of our previous update rule of ICL for the projection can now be seen, like we can see their correspondences now. In the projection, we have the new projection is equal to your previous projection minus the inner product divided by the outer product, the outer product divided by the inner product. And then your new covariance is equal to your previous covariance minus your outer product divided by your inner product, but plus some forgetting factor. This forgetting factor beta t is between 0 and 1, but therefore is now very easy to see that if beta goes to 0, these two update rules are the same. Even though they are derived in different way. One is derived by geometry, the other is derived by this low rank update formula. And then we can continue to see their difference in the model update. In that case, we simply substitute use the previous update rule of ICL, and we now apply this update of theta t to the update of phi t to the update of theta t. So this is the inverse of the data covariance times the covariance of your label and your data. So you will see then the update rule is again the same. There's only one extra term beta t here. So therefore, if beta goes to 0, you get the identical update. And therefore, I think the LS can be viewed therefore a generalization of all the previous algorithms by including a forgetting factor. But the update rule presented here, they are not for practical use. They are like numerically unstable in the sense that if you apply this continually, what you will get is that you will, because you are based on the assumption that this is positive semi-definite, and this projection is orthogonal, has orthogonal columns. But if in the very yield condition case, what you're gonna get is you don't have orthogonality anymore. You don't have a positive definiteness. And this term, for example, can be negative. This quadratic form can be negative, and this quadratic form can be negative. But these are to illustrate their mathematical connection. And I think then, therefore, the history of IS is very much rich. Like we can then connect IS to all the previous methods in this way. First of all, it goes back to the work of Gauss, who did a lot of things, and we are left with nothing to do. So this is a paragraph in the book of this called Inference and Learning from Data of this book. What he said is this step helped him save the trouble of having to solve a least squares problem afresh every time a new measurement became available. So this is basically, I think, the essence of continual learning, namely, you don't want to, at each time you are given new data, you don't want to do it from scratch by retraining your model. Instead, you want to, based on your previous model and your new data, you want to do some update to get a new model. And this is what Gauss thought like 2 centuries ago. And I would say that he's kind of like a continual learner. And then moving forward, we're going to see, and we have seen the connection between RLS and a gradient projection in the linear case. But if you extend it to the layer-wise case, you got the same similar connection. And the story I think is that in reference 1, it was almost 3 decades ago. This survey paper mentioned layer-wise RLS algorithm. That was very similar to the layer-wise gradient projection method. But at that time, the purpose is not to do continual learning. The purpose they have is to train the network faster than LMS with the backpropagation. And then there's a Nature Machine Intelligence paper, reference 2, that was 2019. They somehow applied this layer-wise RLS algorithm that is called enhanced backpropagation to continual learning. And then they can empirically show that it reduces forgetting. Because of this is somehow by design, because your objective is to just minimize the joint loss. And then if you do this, you reduce forgetting. And you can do this in an online way. I think then the contribution of the gradient projection method is that because you have a geometric projection, it is now very easy to derive the theoretical guarantees exactly under some assumptions. But you are going, if you work with this inverse of the covariance, it's harder to derive this guarantee. And moreover, when you have this, when you think about how to update this projection matrix, what you want to have is simply the orthogonal basis, continually updating the orthogonal basis. And this can be done by some very robust numerical SVD methods. So therefore, I think the previous numerical instability can be addressed also by gradient projection. So, and then moreover, this RS algorithm has also some connection to network expansion. To begin with, there is a reference one. What it does is that it wants to grow the network if your loss decreases slowly. Why does this paper 30 years ago wanted to do this? Because they realized that, okay, if you just train a small model, you might not have a good capacity to learn very well. But if you begin with a large model, you're going to, it is going to be very costly. Because you begin with a large model, it is very costly. But of course, this no longer applies today because people just begin with the huge models. Then that was the motivation of this paper. And then what it does is that, okay, let's say, can we reduce the training cost by starting with the small model? And then if we train, if the loss doesn't decrease sufficiently, we just add some new nodes. We extend the width, and then we train it again. So that's the main purpose. At that time, it was the training algorithm is the LMS type, a backup propagation algorithm. And subsequently, I think in paper 2, that was 1993, the authors applied layer-wise RS for that purpose, also growing the neurons. And now, moving forward, we are in our decade. There's a paper just 3 years ago. What they did is to do class incremental learning with the last layer classifier. And in that case, the growing of your neurons is justified by a different way. In particular, in class incremental learning, you are going to observe new classes and new classes. And therefore, your classifier has to output more logits. Say you observe 10 classes, you output 10 logits. But next task has 10 new classes. And then your classifier has to output 20 logits. And this naturally requires your network to grow as you see more new classes. And that paper applies RS for that purpose. And the application is kind of quite like a extension of what we have seen. So let's consider this setup now, which is now very popular. Say we have a frozen pre-trained model that is could be like a VIT or some vision language model. And then what you're gonna do is that you frozen this, but then you do RS using the features, the output features of this pre-trained model. And then imagine that if you have a linear classifier, what you're gonna do is that, okay, at task T, we have 10 output neurons, but then for the next task, I see new classes. I have to expand the output of my layer, and then I get more new logits. To do this by RS algorithm, we simply need to modify the objective a little bit. For example, we now work with matrix rather than vector, because our classifier is, you can think of it like as a matrix. And then the output, so you have this matrix, capital theta. The output, its dimension is, the output dimension is Ct. So you multiply a vector by this matrix, you're going to output the dimension of Ct. And this Ct is the number of classes that you have seen thus far. Therefore, at time 1, you're going to solve this for C1 classes. At time 2, you're going to solve this for C2 classes with the new data. But the RS algorithm changes only a little bit, because when you observe the closed form, you have the covariance between your data and sample, data and the label, and you have the inverse covariance of your data. Because you only change your output dimension, your input dimension doesn't change. And therefore, this term remains completely the same. Only changes is the output label. And therefore, because we are doing like a classification, the output label is like one hot. Therefore, for new classes, we are simply padding. We are simply padding zeros to make the dimension match. So the whole difference is then to how to update this term continually by and at the same time petty new zero entries. Okay, so this is RS. We have seen that it generalizes to gradient projection, generalizes gradient projection by incorporating forgetting factors, and we have seen in history it basically motivates gradient projection. And it works well. It will work well if your ground truth model is shared among tasks up to noise. In the sense, because you are doing least squares essentially, you are somehow requiring you have a relatively nice single model for all tasks, and then you can tolerate a little bit of Gaussian noise. But if say you have 3 tasks, each task is defined by the solution is defined by some plan. They are very different. If you are going to just fit one plan, you are going to never find a good solution to all tasks. You can just find a good solution to one task by linear approach. And therefore, the next topic is to address this problem by incorporating some knowledge about the transfer between tasks. That is the idea of this state space model and the common filter. So here we are going to use some basic probability. So this the name might be confusing. I call it covariance correction because but we are going to understand the means and covariance of all these Gaussian variables. So let's say we have 2 Gaussian variables, that is y and there is omega. Oh, sorry, that is a and omega. Omega is you can think of it as like a zero mean noise, and b is your output, and you have b to be a linear transformation of a plus some omega noise. And from this equation and from the assumption that a and omega are jointly Gaussian, we can conclude that b, your output, and your original input a conditioned on your output observation are also Gaussian. So to be more specific, suppose we have a and we know the mean and covariance of a and omega, we could use some basic probability to calculate, say the mean of b and the mean of a conditioned on b. But for the moment, let's just look at how to calculate the mean of b. Basically, it's simply that you have this equation, b is equal to x transpose times a plus omega, and omega has 0 mean, a has mean mu a. So therefore, you put the expectation on the equation, you get this. For the other equations, it's not very important to remember them, but I think it's important to look at this covariance update equation. And that is why I have the title covariance correction, because we are going to rely on this very much. Here, how to understand this equation? So basically the idea is, okay, originally you have your covariance of A, and then you have a linear transformation, you get some observation B. And given this B, how do you update your knowledge about A? And this formula tells you how to update that. So basically it is your covariance minus this term. This is, we will understand it better, but for the moment, it is simply the correction of your knowledge upon observing new observation, B. This is like already like a very continuous learning flavor, but only we have one sample, like one new observation B. But you will see there's a beautiful relation between all the equations that we have derived. They are algebraically they are a little bit ugly, but they are derived in different ways, and it turns out to be they are very related, even like in some cases equivalent. So let's recall this geometric formula. We have shown this by basic subspace geometry, and we see that your new projection PT is equal to your previous projection PT minus 1 minus some outer product divided by inner product. And in this algebraic formula that we derive using this low rank correction formula for RLS, and we will see that the inverse of the covariance theta T is equal to the previous covariance minus some outer product term divided by an inner product of your data plus some forgetting factor. And then we have just derived a formula that is based on probability, based on Gaussian distributions, and we get pretty much the same formula. So let's simply assume here this covariance sigma b is a scalar. And if that is the case, then x has to be a vector, and then this inverse, you can just simply divide this inverse. And this sigma b is the sigma omega plus x transpose sigma a times x. That is the denominator here. Now, therefore, in this statistical formula, you will see that your new covariance is equal to your previous covariance, sigma a, but minus the outer product of something, as in the geometric formula and the algebraic formula, divided by the inner product, x transpose sigma x. But this time you plus not a forgetting factor, you plus some variance on your noise. That is the variance of omega. So, and then this is the basis for what we are going to do with the common filters. Now we're going to generalize the model to linear Gaussian model, or if you want, is state space model. So previously we have a linear model, yi is equal to xi transpose times theta star. Theta star is a shared model for all tasks. But now it is the right-hand side of the linear Gaussian model is more general in the sense that, first of all, you have the previous equation, yi is equal to xi transpose theta I plus noise bi, but in matrix form, like in vector form. Previously, you have scalar observation, but now you have a vector observation. And moreover, more crucially, you have a new equation defining your model. That is the transfer from theta I minus 1 to theta I, defined by a linear equation. So it says that basically at a task I minus 1, you have a model theta I minus 1. And for a new task, where is the new model? Your new model is theta I. And we now assume that theta I is a linear transformation of theta I minus 1, transformed by AI plus noise. And essentially, then you have a task-specific model theta I. So for T tasks, you're going to have T models. And we are now working on this model. The goal, the one more thing is that we need to assume a bunch of things. So in these equations, we basically assume data xi, yi, they are given, and we are assuming all the statistical quantities, we know their mean and variance. Now we are going to estimate all the models continually. For task 1, we want to estimate theta 1. For task 2, we want to estimate theta 2. But at task 2, we also want to get a better estimate of theta 1. So therefore, let's formulate this MAP inference problem or estimation problem. Basically, we are going to maximize the probability of observing of having theta I conditioned on all your previous data at a time t. That is y1 up to yt. Here we are basically potentially we can assume that I is smaller than or equal to t, meaning that we care about models not only at the time t, but also at all previous times. So similarly as the previous error that we defined, we basically in this MAP estimation problem, we defined a matrix of estimates. So at the time t, we are going to estimate model 1, that is theta 1 conditioned on y1. At task 2, at time 2, we are going to estimate theta 2 conditioned on y1 and i2. But also we care about the previous models. So we will also consider how to compute theta 1, that is the first model, for the first task, conditioned on y1 and i2. I condition on your the data of the current task of the specific task, but also I condition on data of the later tasks. And then to understand this MAP estimation problem better, because what we know is that because Y is Gaussian, and therefore this conditional distribution is Gaussian as well. I'm not going to prove it. And then this MAP estimate is essentially the expectation, because if you plot a Gaussian distribution, which point attains the maximum value, that is your mean, that attains the maximum value. And therefore, essentially, we are going to compute the mean of theta I conditioned on all the data. And the key question is like, okay, we care about all models and of all tasks. The key question is like, how can we say we get a, how can we say about their performance? There's something called a backward transfer, meaning that say, okay, we have this problem of estimating the thetas. Suppose we are now going to solve task 1, 2, 3, 4. And then at that time, we can measure the performance of all the measurements, of all the estimates. For example, this one, what does it mean? It means that the estimate of theta 2 conditioned on the data of 4 tasks, task 1, 2, 3, 4. And what does this mean? Theta 2 condition 2, that is the estimate of theta 2 conditioned on y1 and y2. That is the data of your first 2 tasks. And therefore, essentially, to compare these 2 quantities, we want to know which estimate is better. So intuitively, like a theta 2 conditioned on all 4 tasks is going to be better because you have more samples. You have more samples because you have y1, y2, y3, y4. But these samples are from different tasks. You have only, for task 2, you have only samples from task 2 that belongs to you, like M samples. But the data of task 1, task 3, task 4, they are for different tasks. So this is not very clear. Like how can you compare them? So to do this, let's define some metric. That is the error covariance. Like that is the estimate. Suppose at time t, you're going to have an estimate theta I, and then you just take the error covariance. The expectation is taken over theta I, and then you will see that the trace of this error covariance is equal to the quadratic squared error of your estimate and the true model theta I. So because so now if we see that this if this covariance at the time little t is smaller than the covariance at time little s, and then what we can conclude is that at the time t we have a better model because the squared error is smaller. What we're going to do, therefore, is to show that whenever we have more tasks, t larger than I, we want to show that we have smaller error covariance, meaning that the error covariance at a condition on data of all task t is smaller than or equal to the error covariance conditioned on just the first I tasks. And for this, I want to show you some empirical observation first. That experiment is from the book of Kevin. And what it shows is that, say, it was described in linear dynamical system language. But the point is, you have this figure plots the covariance of estimate I conditioned on just the first I tasks. And then you will see that this circle, the radius of this circle represents the uncertainty or the error covariance, how large it is. The larger the circle is, it means that it's less certain, means that the error covariance is larger. So, and then this plot computes the value of error covariance for for estimate I conditioned on t tasks. T is larger than I. And then you will see that the error covariance is smaller because the circle is smaller. This is an empirical observation. I looked at the book, there's no proof. I looked at the other references, there's no proof. So, and then we're going to do I think we have some time to maybe finish this proof, but we are, okay, so hopefully we can arrive at that. The point now is that we are first step 0. That is, we are going to understand the basic mechanisms behind like how to compute all these error covariance. If you don't know how to compute them, then you don't know how their relationship is, and then you don't know how to prove this inequality. So this then refers to the classical common filter algorithm. So the common filter algorithm starts with this point, that is your original covariance, you know nothing. You condition on 0, you know nothing. But then at task 1, you are given one task, one sample, for example. You are going to update your covariance. And then you follow this trajectory to compute all the covariance. And the purpose, therefore, of the common filter is to do tracking. So you track the covariance at a time t based on all data at a time t. And then on the other hand, the smoother, what it does is to go backward. Say, is like to start from your most recent estimate, you go backward to compute the error covariance of your previous estimate. And I think we are going to talk about this algorithm a little bit, but now let's observe a very, very basic thing. So you will see that why don't we, like, for example, if we want to compute theta 1, conditional theta 2, conditional 2 tasks, why can't we just start from here, we draw error here, say we can compute this. But the point is, like, we can do it because to compute this error covariance, what do we need? We need the Y1, Y2, that are the observations of the first 2 tasks. But yeah, if you rely only on the covariance of one condition, your Y1, you're not going to do it correctly because you don't, this covariance and this mean has no information about your new data. So basically, in some sense, we are forced to follow this trajectory. And then the prediction step is quite simple. So basically, now I modified the Gaussian linear model a little bit. It's the same as before. The notation is complicated. What's the difference is that I conditioned on all previous samples. So we have the previous equations. We put a condition on the previous samples. We get the same equation. Only in that our random variables are different. For example, now our random variables is theta j conditioned on all previous y's. And our observations is yj conditioned on all previous observations, but it's the same equation. You just have some conditioning. And therefore, to predict the covariance, this is basically the formula we have seen, but only that we have just the extra conditioning. And similarly, if you remember, if you don't forget what we talk about how to do variance correction, we are going to have this kind of formula because, so now at this point, what are we doing is that, okay, theta j, that is the j's estimate of the model, conditioned on j's tasks, all j observations, is going to be equal to the same model conditioned on one less task or one less observation. We have done this before because we incorporate a new observation by updating the conditional by condition on it. So it is the same formula, even though these equations are like algebraically complicated. So the only lesson that we want to know from this common field update is that this equation holds. Meaning that by incorporating a new observation, you are reducing your error covariance for the current for the model J. Okay, and then this I'm not going to prove is there are more algebra right there. But the point is, you have this proposition like saying if this inequality holds at say estimate 3, you can run this smoother to propagate this inequality here. So, and then this inequality holds for model 3, and then it will hold for model 2, and it will hold for model 1. That's what this equation says. And then we can then put these two equations together. What we're going to get is we're simply going to replace this term by sigma jj. And by doing this replacement, we simply, previously, we propagate the error covariance by by pointing upward. But now, because we replace the theta j condition of theta j minus 1 with the theta jj, and we just shift the 0. So this now pointing towards the diagonal. And here we point upwards still. And then you would have a nice propagation property by doing this, because if you're at this point, you only have one error covariance. The equation already holds. For example, if this is 4, 4, 4, 4, 4, 4, the equation already holds. And then you're going to propagate and propagate. So we then, of course, we're going to apply this for j equal to t minus 1 up to I, we get our desired result. This result is just saying that once we have more tasks, even though they're from different model, you have new more observations, even though they are from different tasks, you're going to improve your estimation. So now we have seen that the quick summary are going to finish. The optimal MAP estimate can be computed by common filtering and smoothing. And this results in positive backward transfer because we have reduced error covariance. And moreover, we can prove positive forward transfer, and it is easier because the forwarding equation is easier. This requires the task relationship between two tasks to be known, because we need to know AI that is the transfer between two tasks. And then I'm concluding the talk by testing how much you have forgotten. So basically, we have described all these algorithms, but sometimes some of them like described in a rush. But basically, they have all these connections. They are algorithms designed for linear models or linear Gaussian models. The algorithms designed specifically for deep networks or for linear models. They are connected in a nice way that you start from linear models, for example, can derive the other algorithms. I think that's the main message. Even though you started from a very simple setting, you are going to get practical and applicable algorithms, and potentially even with some theoretical guarantees for deep networks. And moreover, so we have this figure. Hopefully, it's understood now. For the first part, we show the connection between LMS and the continual regression. And this is now motivating a lot of optimization theory development that is motivated by like continuous learning setup. And then for the gradient projection approach, they are motivating a lot of large language model works on knowledge editing, because what you know is that when you edit your activations or your knowledge in the latent space, if you do this based on some orthogonal space, you're going to not forget your previous knowledge. And the network expansion part is that we have seen how this idea works in the past, and then we have LoRa and a lot of classic continuous learning expansion methods. And we have seen that common filters can produce a positive transfer among tasks. But this is only for the linear case and for the case where you know the task relationship. And there are like interesting theoretical works to be done to extend that. The final remark that we want to make is that this tutorial is only about the past, like how past connect to the present. And there's a famous quoting that has some implicit political meaning, saying that who controls the past controls the future. and who controls the present controls the past. So by replaying this saying, we want to say that like by understanding the past and the algorithms better, we are going to do a better innovation for advancing the continued learning frontiers. Yeah, thank you very much. I think I finished.
Any questions? So I have a question then. So a lot of your work is, or a lot of the tutorial you present, it's about projections. So those are like some kind of hard constraints. Can you imagine like where soft constraints would come into play? Because like a lot of the continual learning algorithms do not exactly use projections, but they more act as a regularizer. So there's like a soft constraint in terms of the.
And this is the next question is like refers to how do you balance the past and the present. So I think there are some, for example, even just for gradient projection, what you can do is that say you typically if you remember the past too much, you couldn't learn anymore. And the way that we could do is that we just take the top eigenvalues or top components of the subspace. So we keep a low rank subspace so that we have enough capacity to learn new tasks. That is one way to think about it. And then there are, I think there are ways to, this thought could be also incorporated in network design. For example, like if you do LMs like DataNet in SSMs, you're going to tracking very greatly. But if you do some least squares type thing in network, you're going to do recall greatly. But then how do you combine them together? By come up with a new architecture for that. And I think this is a good direction.
Oh, thanks.